section of this module, that is the geometric dual. Now consider the plane representation of a graph with 6 regions or 6 faces. That faces are denoted by F1, F2, F3, F4, F5, F6. Okay, these are the 6 faces or regions of a plane representation of a graph. Now here we consider 6 points also, P1, P2, etc. P6. Consider 6 points in each of these regions. Here P1 is in the region F1 and P2 is in the region F2, like that. Now here we join these 6 points in the following way. That means if Fi and Fj are adjacent, if Fi, if we consider the ith face and the jth face, if these two faces are adjacent, that is if they have a common edge, we draw a line joining points Pi and Pj that intersect the common edge, between Fi and Fj exactly once. If there is more than one edge common between Fi and Fj, draw one line between the points Fi and Fj for each of the common edges. For an edge E lying entirely in one region, say Fk, draw a self loop. So that means if an edge E is entirely in one region, that means Fk, then that edge become a self loop in its dual at a point Pk, intersecting E exactly once. By this procedure, we obtain a new graph. That graph is denoted by G star, consisting of 6 vertices. What are the 6 vertices in the dual here? P1, P2, etc. P6, and of edges joining these vertices. Such a graph G star is called the geometric dual or simply a dual of the given graph G. Clearly, there is a one-to-one correspondence between edges of G and G star. One edge of G star intersecting one edge of G. Now we can consider what are the relationship between G and G star. The first property is an edge forming a self loop in G is a pendant edge in G star. So a self loop in G, become a pendant edge in G star. So self loop converted to pendant edge. Now what is the second property here? A pendant edge here. The pendant edge in G converted to a self loop in G star. Now what is the third property? Edges that are in series. Become parallel edges in G star, and parallel edges in G become series edges in series. So the fifth property, the general observation that the number of edges constituting the boundary of a region Fi in G is equal to the degree of the corresponding vertex pi in G star and vice versa. Okay, now the property 6, graph G star is also embedded in the plane and is therefore planar. Seventh property, seventh property is considering the process of drawing a dual G star from G, it is evident that G is a dual of G star. Therefore, instead of calling G star a dual of G, we say G and G star are dual graphs. Now, the eighth property, if N, E, F, R, mu represent the number of vertices, number of edges, number of region, rank, nullity of a connected planar graph of the graph G, and correspondingly there exists N star, E star, F star, R star and mu star corresponding to its dual G star. Then what is the relation between these? Then the relations are number of edges of G star equal to number of faces, and E star is equal to E, F star is equal to N, R star equal to mu, and mu star equal to R. Okay, so these are the relationship between G and G star. Now we can consider one example 2. Okay, so consider one figure now. Suppose here is one vertex. Now we can join these 8 vertices. Now we can mark the faces like this. Suppose this is our region 1 denoted by F1. This is our region 2 denoted by F2. This is our region 3 denoted by F3. This is our region 4 denoted by F4. And this is our region 5 denoted by F5, that is a self loop. And the outer region, that is a big region, that is denoted by F6. So here there are 6 regions. Okay. Now this is our figure A. Now we can mark 6 points also here, denoted by P1, P2, etc. P6. So we have to redraw this figure once again. Okay, this is our figure. Now we can mark the points here. This is P1. Okay. Now this is our point P1. Now in here P2. Then here P3. Here P4. Here P5. And here P6. Okay, 6 points are marked. And this is our figure B. Now we can join these points. How? Here we can see that here these P1, this region and this region are adjacent. So there must be an edge from P1 to P2. So adjacent regions are connected by edges. Adjacent edges are adjacent regions are connected by edges. So let us see how we are connecting the edges here. So from P1, here F1 and F2 are adjacent. What are the adjacent faces of F1? F1 to F2. F2 is adjacent. Okay. Then F3 is, is there any common region between, no, there is no region between F1 and F3. Then F1 and F4. So P1 to P4. We want to mark the edge. Then from P1 to F6. P1 to P6. So mark the edges in this way. That way one edge is there. So F1 to F2, F1 to F4, F1 to F6. Okay. Then here we can see that this vertex, here this vertex is pendant vertex. So we have to draw a self loop in the dual. So we want to draw a self loop. This is the self loop here. Now we can consider our F2. Now F2 and F1 is adjacent, that is already drawn. Now F2 and F6. So we have to draw from P2 to P6. Draw P2 to P6. Then F2 and F3. So P2 to P3. Then P3 and P4. So P3 to P4. Draw an edge. Okay. Then you have from F6 to F1, F6 to F2 already drawn, F6 to F5, F6 to F5. Okay. Then F6 to F4. That means P6 to P4. Okay, P6 to P4. Okay, now these are the edges in the dual. So all duals of a three connected graph are isomorphic. All duals of a three connected graph are isomorphic. So using the rules already listed, we can draw the dual of any given graph. Okay. Now, thank you all.